Finished with this last time, and if you remember, the instructions for number 6 were, decide if this series converges or diverges, and if it does converge, decide if it is conditional or absolute. So, did you guys get to this one? I feel like maybe a couple folks got to it, but not everybody did. So if you didn't get to it, let's go ahead and consider this. This will be probably a good review, kind of connecting last time with this time. So check out number 6, and then we'll move on to our final convergence test of the year, of the chapter. The solution of this one, number 6 here. First of all, we're just going to look at the series as is. Do you guys recognize that it's an alternating series? Hopefully you saw this little element here on the top that indicates that it's going to be an alternating series. And so we can identify it. We probably want to identify it like that. So we'd say this series is alternating. And if you do the limit as n goes to infinity of 1 over ln of n plus 1, what do you get? 0. Yeah, okay. So that's good news. And did you see a consistent decreasing pattern in those terms? As you went, n got bigger, the terms got smaller. Yeah, so we'd say, the terms decrease in absolute value to 0. And so, by the alternating series test, the series converges. Okay, so as is, the series converges, but we were asked to then analyze a little bit further if a series converges. Is it an absolute convergence or is it a conditional convergence? So how do we decide this? Like, what was our first step to decide if it's absolute or conditional? Absolute value, right? Take away the alternating piece. So we'd say something like sigma from 1 to infinity of absolute value of that series really is just this. Okay, so now we got to decide if we take away that alternating element, what happens? Does the series converge or diverge? Good morning. So, I don't know. You look at the remaining series there, and the nth term test is going to tell us nothing. We kind of already know that from before. And it's not a geometric series. Did anybody think to try to use like an integral test?
We tried, but we don't know how to.
Yeah, it's not very pleasant, right? Because the ln's in the denominator. So I don't know that integral test is a good way to go. It's definitely not a p series. So what are you sort of left with? Some kind of comparison. What did you compare it to? Did anybody arrive at a good comparison? Sorry? Yeah, the basic harmonic series, I think, works okay. So let's think this through. If we're going to set up our comparison, we're going to say 0 is less than, I guess it would have to be 1 over n, which is less than or equal to 1 over ln of n plus 1. That's the correct comparison right now. Is that true on 1 to infinity? Let's see here. No, it's not true on 1 to infinity, because if you start off at 1 over n would just be 1, whereas, no? Yeah, that is barely true, isn't it? Yeah, because ln of 2 would be slightly less than 1, so when you copied out flop, it would be slightly more than 1. Yeah, that works, doesn't it? Right away. Okay, cool. So I'll just say on 1 to infinity. Okay, so now we've got it set up, now we can finish it. So since that relationship is true, we know that sigma from 1 to infinity of 1 over n does what? Diverges, yeah, and the reasoning there could be p-test, could be integral test, could be harmonic. Right, so harmonic series, they always diverge. And so therefore, our original series diverges because it's always above, right? So if 1 over n is too slow, then the one above it is definitely too slow. We can say, therefore, by comparison, our original series diverges too.
Mr. Anderson,
Uh-huh.
can you please explain the second subject, the 0 is less than 1 over n, which is less than or equal to
Yeah. So let me finish this statement really quick. So also diverges, therefore the original series is conditionally convergent, right? If you take away the sign changes, you get a diverging series. If you include them, you get a converging series. So we'll say conditionally convergent, which is kind of the original question. Okay, so Grace, you were talking about this right here.
Yeah.
Are you talking about why we put that there or why that's true?
Why we put it there.
Okay, yeah. So I kind of ran through it kind of quick. Let's go back through it. When it came time to say, all right, does this series converge or diverge? You have to kind of go through like your list of options, right? So nth term test tells us nothing. It's not a geometric series. It's not a p-series. Integral test, try as you might, I don't think it's going to work very well. I feel like I'm forgetting one of those for some reason. But you go through all those tests and you're like, all right, none of these really works. You finally arrive at comparison. So to set up a comparison, you have to set up some kind of an inequality expressing the relationship between the series that we're concerned about and the one that you want to compare it to.
Okay.
So the series are supposed to be positive, right, both of them. And one of them needs to be bigger than the other on like the tail end. So from like 1 to infinity or 10 to infinity or whatever, like that far right end, we need to have a consistent relationship where one is always above the other. So the line of thinking is, once you get this set up, if you know that this series right here diverges, because the divergence or convergence is essentially a question of, does the series approach 0 fast enough? Right? That's the question. So if that series, if that 1 over n doesn't get there fast enough, then any series above it wouldn't get there fast enough either.
Okay, so if it would converge, you would want
This one.
to lift.
Yeah, you more or less. So, not that we would compare anything probably to 1 over ln of n plus 1, but if that series converged, we'd say, well, hey, the one that's higher, if that one gets there fast enough, then the one that's lower
Okay.
would get there fast enough too. You can't flip it around though. You can't say something like this one. I know it doesn't, but you can't say 1 over n converges. Therefore, the one that's higher than it also converges. That may or may not be true, but this doesn't prove it.
Okay.
That make sense?
Yeah.
Okay. Good question. Anyone else with a question? Okay. I hope that was a good tied all together sort of thing. We did a lot of those. It's a newer topic for the AP framework. Okay, so we're all good. Welcome. Sorry you missed it. There's a 8-minute video you can watch. There you go. All right, so let's do our last. And this is an interesting one. Like I said, we'll use this one a lot. So the ratio test has a couple of conditions here. So here we go. The series with non-zero terms. And then here's the test itself. So the series converges absolutely if that limit, and we'll talk about what that limit is here in a second, is less than 1. Diverges if that limit is bigger than 1. Obviously infinity being bigger than 1 fits that category, but I want to make sure we all understand that that's part of the game here. And then finally, the ratio test is inconclusive if you get exactly 1. So if you do this limit, you get less than 1, absolute convergence. If you do the limit and you get something bigger than 1, diverging. And inconclusive if you get exactly 1. So let's talk about what this limit is. It was the same in each statement right there. So it's the limit as n goes to infinity of absolute value, so we're disregarding any alternating stuff. But then the ratio in there is a sub n plus 1 over a sub n. Any ideas what that means? A sub n plus 1 over a sub n. Could you say that again, Hayden?
Just add 1.
Add 1 to what?
Your equation on the top.
Well, like the next term is going to be.
That's more what I was going for. We do add 1, but that gives us the next term, right? So if you take like the next term divided by the current term, that's our ratio. So if you think about this, if you think about maybe the middle one, if we think about this ratio right here, and we think, okay, so that's next term divided by current term, and you get something bigger than 1, doesn't that mean that the series terms are getting larger? Yeah, so you almost, if you were astute enough, you could even just use an nth term test to show that too. But then you will, if you want, I can show you a couple of situations where this ratio test is inconclusive. But if you get a number that's less than 1, it means it's decreasing fast enough, right? So the next term is getting smaller fast enough where you get a series that converges. And I think this little statement over here is something really to consider. If your nth term has some kind of a factorial in it, the ratio test is probably going to be the way to go. We don't want to do any crazy comparison tests or stuff like that with factorial. And integrating factorial at this point of the game is a non-starter. It's definitely not a p-test. I mean, you're kind of going to work your way back around to using the ratio test anyway. So if you see an exclamation point, think ratio test right away. Yeah.
So a sub n plus 1 over a sub n means you bring like a sub 2 over a sub 1?
Yeah. Yep. So one term in the bottom, the next term in the top. Yeah. Okay. So let's try this out. There's going to be some pretty interesting arithmetic. I hope you guys will be entertained by it. I know that I am. So here we go. Let's take a look at number 1. We were asked to use the ratio test to determine convergence or divergence. And so we're going to set this up. And here's how this works for number 1. We're going to say the limit as n goes to infinity of, I want to mention this, all those limit as n goes to infinity, they're all listed as fractions. I'm going to tell you right now, I'm almost always going to just automatically do copy.flop. I'll show you what I mean by that here in a second. But we want to know the n plus 1th term. So I'm thinking that would be this right here. 2 to the n plus 1 over n plus 1 factorial. That makes sense? N plus 1th term? And then I'll extend this absolute value down a bit, and I'll show you what I mean. What I would typically do here. Divided by just the nth term. So that would be what we already have to begin with, 2 to the n over n factorial. So this is the setup for the ratio test. I can't think of a situation where I would ever write exactly that. Can I show you what I would normally write? Hopefully you'll do the same. I'm going to erase all this stuff. You can look at your page and see that I would normally just write this. Limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. Does that make sense? Just automatically do a copy.flop. Definitely counts as the ratio. Please don't feel like you need to write that fraction. Where did I get the 9 point something? You're good? I didn't catch that either. Okay, so before we can proceed, we got to do a little bit of simplification here. I see some simplification between this and this. So the bases are both 2's, right? So if you have a base of 2 with an exponent and a base of 2 with an exponent, and you're dividing them, what do you do with the exponents? You subtract, that's right. So n plus 1 minus n is just 1. Yeah, okay, so I'm going to write this now as limit as n goes to infinity. Still got the absolute values in there, but the 2 to the n plus 1 over 2 to the n is just going to be a 2 in the numerator. Does that work? We still got the n factorial and the n plus 1 factorial, and to help us with this, I'm going to write it out a little bit. Let's check this out. N factorial would be n times n minus 1 times n minus 2 dot dot dot, right? And then n plus 1 factorial would be n plus 1 times n minus 1 times n minus 2 dot dot dot. So what's going to cancel out? Yeah, the n plus 1 will remain, but this would cancel with this, and this, and this, and this, and this, and the dot dot dots, those would all cancel, leaving you simply with n plus 1. It's a pretty big bite, but you can really take out a big chunk of it in one shot there. You guys have any questions about that? That line of thinking is very common. Very, very common. So if you've got a question at some point today, please ask.
Can you just, I don't know, can you just like kind of go over how you got that again?
So what I essentially did is I expanded out what factorial means. So factorial means whatever number it is, times the next one down, times the next one down, times the next one down. And so what I did is I tried to take
Down, isn't it? Up?
factorial, no, so like 5 factorial.
Oh, yeah, that's true. Never mind.
5 factorial means 5 times 4 times 3 times 2 times 1, right? Does that make sense? Okay. So then what I did is I said this n factorial is the same as this, including the dot dot dot, because we don't know exactly where it would end, because n is some unknown number. But if that's true,
See, and then you minus one from the bottom as well.
expanded both,
Okay.
and then canceled the common elements.
Yeah. Okay.
Yeah. Thanks for asking. I mean, I don't know, what might appear to be obvious is not always obvious, right? Thank you for asking. Yeah, Mackenzie, go ahead.
Okay, wait, this feels kind of dumb, but, so, for the first part,
Yeah.
why did you, like, do the 2 to the n plus 1? Like, why did you do, I understand you did the, caveat flop, but like, how did you get that equation in the first place?
The n plus 1?
Well, like, the 2n plus 1 over n plus 1 factorial
Yeah.
divided by
Sure.
2 to the n.
So that comes from this right here. It comes from what the ratio test is.
Oh, so you just kind of plug it in?
Yeah, so I'm plugging in like essentially, so like a sub n plus 1 would be like the n plus 1 term. So it's like the next term out in the future. And the a sub n term, that would be our current one. So whatever a sub n is, n plus 1 is just the next one. And we don't know which one we're talking about. Are we talking about like the 7th and 8th? Who knows? Are we talking about the 1st and 2nd? Possibly. It really doesn't matter. We're just talking about a term and then the next one. But we're doing it very generally.
Yeah, that makes sense.
Is that okay? Did I explain that? All right. Anybody else? Let's try to clear up any misconceptions, questions of any kind, as best we can. Okay, so we're ready really to finish this. So we'd say limit as n goes to infinity of 2 over n plus 1 now. We can make a judgment on this. Equals what? 0. Cool. And what is so important about 0 here? It's less than 1. Okay, so since we got that limit of 0, which is less than 1, we can say therefore by the ratio test the series does what? Yep, series absolutely converges. I think if you just put converges there, I think I'd be okay with that, but absolutely converges is the case. All right. So as long as you can handle that kind of crazy arithmetic, you can do this, right? Any follow-ups before we move on to our next one? Okay, awesome. Check this one out. Okay, so for this, I'll tell you what, let's do this in little pieces. Let's see if you guys can set up your ratio first, right? And this is kind of what Mackenzie was getting at, like, hey, how do we get this thing? Let's try to set that up first. So take a look at number 2, and let's try that. Ready to go. And we can kind of go from there. So we would go limit as n goes to infinity of, there's a bunch of n's in there, right? So all of those n's need to become n plus 1s for this to be the n plus 1th term. So it would look like this. N plus 1 squared times 2 to the n plus 2. Is that okay? All right, n plus 1 plus 1. Okay. Divided by 3 to the n plus 1. Instead of dividing, we're going to just multiply by the reciprocal. So copy dot flap. So it'd be times 3 to the n over n squared times 2 to the n plus 1. Okay. Now, some arithmetic. Here we go. What do we do with the 2's? There's two 2's. How do we handle those? Any suggestions?
You can, if you change back to n plus 1,
Mm-hmm.
you could, like we did earlier with the, 2 to the n plus 1 and 2 to the n, we can cancel the 2 to the n plus 1s, and then in the numerator, we just get 2 to the 1, and it's just 2.
Yeah. Yeah, subtracting out the exponents, exactly right. Two in the top. I totally agree with you there. Okay, and then how about the 3's? Same kind of an idea, right? Except 3 would be in the denominator, right? There's one extra 1 in the denominator. So I'll put 3 right there. Is that okay? All right, and then the other stuff, maybe not as easy. N plus 1 squared, n squared. We can't just conveniently cancel stuff out like that. So what I'm thinking is, I'm going to take that n plus 1 squared and FOIL it out. So
Why is it n plus 1 squared? It's not n squared plus 1.
no. So when we set this ratio up, what we do is anytime we see an n, we replace it with n plus 1. Is that okay?
Yeah.
Okay. All right. And I suppose if we wanted to, we could do one of two things here. We could either distribute the 2 across the parentheses and multiply the 3 in there with the n squared, or we could just get it out of there. We could just say this is equivalent to 2/3 limit as n goes to infinity of n squared plus 2n plus 1 over n squared. And at some point, we got to deal with the limit, right? So what do you think that limit ends up being if we go to infinity? You could do two different ways, right? What are the 2 different ways you could do this? Coefficient thing, right? Because the degrees are equal, right? Or couldn't you do L'Hopital's? If you really wanted to. Now, L'Hopital's is definitely slower, but you could. Bottom line is, what do you get? 1. And then, of course, times 2/3. 2/3. What is so important about that 2/3? It's less than 1. Okay, awesome. So less than 1. So our conclusion is similar to before. We can say, therefore, by the ratio test, the series converges. Absolutely. Question, Hayden? No? Okay. Okay. So with number 1, kind of showed you. Number 2, you did part of it. Try number 3 by yourselves. Good on this one. So we set up our ratio because we're asked to use the ratio test. There's not much suspense on this one. So limit as n goes to infinity. And our n plus 1th term would be this. N plus 1 to the n plus 1 over n plus 1 factorial. So any place you see an n, you write n plus 1. Times just the reciprocal. I'll let you keep going. Did I start too soon? Oh, okay. Okay, well let's finish it off. You guys okay with that ratio? That all made sense? All right, so let's do some arithmetic and hopefully a lot of good canceling and stuff like that. Looking at the n's, the n factorials, that's pretty clear based on what we did at the start. So our I think we could cancel, we could write it out like this, I suppose. We could have n factorial up here, and then we'd have n plus 1 times n factorial down there. That make sense? Okay, so this would cancel with this. But then what about the other n's, right? So we've got n plus 1 to the n plus 1 over n to the n. Any thoughts on that?
You can split up the exponent and do n plus 1 to the n times n plus 1 to the 1.
Ooh, interesting. Okay, so let's keep going with that. And the concept there, of course, is if you're adding exponents, you're really multiplying bases. Yeah, okay, good. So limit as n goes to infinity, and it would be, as mentioned, n plus 1 to the n times n plus 1. We still have n plus 1 down here, and we still have n to the n down here. But this allows us to clean it up a little bit, right? So it would be this and this. Okay, so we still got the to the n's.
Did you like do a thingy?
The thingy sounds about right. I'm not sure what you mean by the thingy.
A fraction. A fraction all to the n.
Oh, sure, yeah. The thingy sounds pretty good now, yeah. We'll go with that. Okay, so if you take these two right here, as she mentioned, if we're taking both to the nth power, you could just write it as a whole fraction to the nth, right? Okay. So I'll write it as n plus 1 over n all to the nth. Yeah? Anybody get past this? Anybody go any steps further? You guys are getting really far on this. This is great. There might come to be a sticky point in here somewhere. That's okay. Anybody go beyond this? So did every person get stuck either here or earlier? Nobody went past this. Okay, that's okay. I'm fine with that. This is definitely a challenger. So here's what I would do. That fraction, n plus 1 over n, I'm going to split it out, right? So you can split the numerator. Couldn't you rewrite it as essentially n over n plus 1 over n? I'll write that out here. N over n plus 1 over n, still all to the n. Okay.
At least one.
Yeah. So this is where we've seen this one time, maybe twice. Maybe you've seen it more than that, just on your own for some reason. This is actually the definition of something. And I put this in here. I don't know if you guys recognize. Did you see the n to the n is really the x to the x? The thing I told you we wouldn't really deal with. So this is a little bit beyond, but I thought I'd push you a little bit. See, if you can do all the n plus 1 and the factorial stuff, then I think this will have served its purpose. But to finish this one, I don't know, maybe a little bit past where we need to go. It is, for sure. Does anybody have any idea what that is? That's a very special thing.
It's infinity plus 0.
But to the infinity. We've looked at this
0 to infinity is a little bit tall.
one time. Yeah, it is. Yeah. Well, 1 to the infinity is 2.
But a 0 to infinity is a little bit
That's infinity.
tall.
No.
Oh, it's the, it starts with an R.
No?
I think I remember when we looked at it, because we were like, this is what.
Starts with C.
It does start with a letter, though. And amazingly enough, it starts and finishes with the same letter because it's a single letter.
A.
E. C. D.
E. Good guess. Yeah. Yeah, this is actually the definition of E.
Oh, I knew that.
Yeah. But you know, like the E on your calculator, right? The natural log base. So this is the definition of E to the first. So this is not a step I would expect you just to come up with on your own. I just thought, hey, you are all smart people. I'll push you a little bit. See how far you can get. And you guys got pretty stinking far. I thought that was pretty good. Pretty good effort.
Basically, what you're telling me is that whole thing boils down to 1.
It ends up being 2.71828 ... E to the first.
So it died.
So the important thing here is, of course, that number is bigger than 1. Therefore, by the ratio test, the series diverges. Okay, so please don't get too wrapped up in all the details. What I am concerned about with number 3 is, can you set up your ratio? Can you do all the cancelings, things like that? If you get to this point that I'm underlining right here, and you weren't sure how to move beyond that, I'm okay with that. I'm not going to be assessing you on stuff like that, but I want to make sure that you know how to do all the cancelings and manipulations with algebra, stuff like that. I think that's kind of the point of number 3. We'll come back to more of a normal sort of a deal with number 4. Question though.
So I also got diverges, but I stopped at when we got to n plus 1 to the n over n to the n, and then I just saw that the top would always be bigger than the bottoms, and it would be greater than 1. Does that work?
I think that's pretty logical.
Okay.
Yeah. So I think that's pretty logical. I think you'd have to use some words to explain yourself, perhaps, but yeah, that's logical. Yeah. Okay, number 4. Let's check this one out. We got about 5 minutes left, and I think that'll be enough time for us to get this done. Let's check it out. Feel free to look if you want. So, did you guys set up this ratio?
Yeah.
There really wasn't anything that could be canceled out, though, was there?
Yeah, but so I think about a dual because
You could. I
got infinity over infinity.
don't think you really need to do L'Hopital's rule, though, to be perfectly honest.
Why? You have infinity over infinity.
I didn't say you couldn't. I just said you don't have to.
But you can't simplify.
You could. You really could. So I'll show you what I mean.
Me and Al will go.
So check this out. We get really good at taking things out of radicals, don't we?
Yeah.
Hello? Yeah? We can put things back into radicals too, can't we? So that's what I'll do here real quick. I'm going to take that n plus 1, I'm going to put it back in to the radical. So it'd be limit as n goes to infinity, absolute value. For this to go back in, we got to square it, right? So it would end up being root n plus 1 cubed.
And that, like, I did it a little bit differently. That would be the same as to the 3 halves, right?
Yes.
Okay.
Yeah. And then down here, it would be root n times n plus 2 squared. Remember, if you've got a squared in the radical, you can take it out by just dividing the exponent by 2, right? You can put it back in by multiplying by 2. So, I think at this point I can make maybe one more move and say limit as n goes to infinity of big square root of n plus 1 cubed over n times n plus 2 squared. Now here's the most important thing about this, is that the degree in the top is 3, right?
And the degree in the bottom is
3. Because it would be n squared plus 4n plus 4, but then times n would give you
3.
n cubed, right? So if the degree in the top and the degree in the bottom are the same,
You take the ratio and they're both going to be
1, and the square root of 1 is 1. So what's interesting about this is we get 1, and what does that mean?
nothing.
It means the ratio test is inconclusive.
It's not enough.
So we'd have to use a different test. And so let's just finish with this and then we'll go. If you were going to use a different test, what test would you use?
The
Alternating series test? Can anybody see what the alternating series test would tell you?
that you should.
What's that, Jasper?
We should probably use it in the first place.
Probably do what?
Use it in the first place.
Perhaps. This said use the ratio test, so we at least follow the instructions. What do you think the ratio test would tell you, though? converge or diverge? Can anybody see it? Say again?
No.
Alternating series test would definitely tell you converge.
Why?
Because you do limit as n goes to infinity, you'd get 0 with an alternating element. Terms decrease in absolute value to 0. You would get converge for this.
You get root infinity over infinity plus 1.
It would definitely be conditional convergence. It would not be absolute convergence, but conditional, yes.
Infinity over infinity.
I'll show you the details if you like. All right, so please remember, as mentioned before, you've got your Loop Quiz 3 on Monday. Have a great weekend. I will see you then.